Hello, calculus students. As a review session, I'm going to use the actual exam problem I wrote. I wrote this exam in, I forgot exactly what semester I wrote this, but it was the actual exam problem that I used in the past. And it is structured like this: two limit computation problems, and then some graph problems regarding limits and the derivative, and then the derivative computation problems, tangency problems, and then a wildcard. The structure of your exam will be similar. Of course, not the same, but many of the problems will be recycled here with some elementary change. For example, limit computation problems and derivative computation problem, they don't go anywhere. So they will have to come back. Okay, let's go to my notebook and let's study those. This kind of problem is almost certain. We have a 0 over 0 type limit. If you plug in x equals to 2, you're going to get 0 over 0. Now, how do you handle this kind of problem? Let's see. We have fractions, so I'd like to have a little bit bigger font. Okay, I guess that'll do it. All right. Method number 1 is to factor and cancel out the 0 factor. And here we go. I guess the font was too big, or maybe this was just too long. Excuse me, let me fix this. Okay, and then, all right. Okay, and then this one. Didn't have to go that much. Okay, and then finally this. Okay, now it's safe to increase the font. All right, here we go. First, we factor the numerator and denominator. The numerator is quadratic, but it's trinomial, so you can use the typical factorization technique for quadratic trinomial. Factor of this -8 must add up to the middle coefficient -2, so we get -4 times 2. That's elementary. And then look at the denominator. We have GCF out, x out, and what's left is quadratic trinomial. You can factor this. It's non-monic, so it's a little bit tricky, but you can do it. Now let's go to the next step. Factorization of the denominator is non-monic, so you may have to use tic-tac-toe method, which I usually use, or any other method. In any case, you can factor it. How about the numerator? You have x squared plus a positive number. That's irreducible. You can't do anything about it. But x squared minus something, we can use x squared minus a squared. X plus a, x minus a. You can use that. So x minus 2 and x minus 2 cancel each other out. And now we have this limit computation. It's not 0 over 0 anymore. We don't have 0 in the denominator anymore. So you can just plug in x equals 2 and do the computation. And this is a textbook's method. Another way to handle it is to use L'Hopital's rule, which I did not actually cover yet. But it's useful, so let me mention it. Simply take the derivative of the numerator and denominator, and then now you can plug in the numbers because it's not going to be 0 over 0 anymore. If it's still 0 over 0, then you have to take the second derivative, and that's still 0 over 0, and those derivatives, and so on and so forth. Sometimes it works, and sometimes it fails, and this is one of those examples that it works. If you have 0 over 0 type limit, or sometimes infinity over infinity type limit, you can use L'Hopital's rule. This is something we're going to study in chapter 4 of our textbook, and of course in the second half of the course, but nobody is preventing you from using chapter 4 technique in chapter 2 problem. It's okay, so you can use it if you want to. Let's go to the next limit computation problem. Now we have infinity over infinity type limit, and we have some radicals here. Okay, how do we handle it? The best way to handle it is to use the asymptotic estimation. The numerator is asymptotically equivalent to this numerator because x to the fourth power is much bigger than these, so I can cancel those out inside my square root. And then x squared is much bigger than this one, so I can cross this one out. As a matter of fact, 9x to the fourth power inside the square root has growth order of 2, which is equivalent to this. So yes, the numerator has growth order of 2. Same goes to the denominator. The 7x plus 1 is not important because x to the fourth power is much bigger inside the square root. Fourth power inside of the square root equivalent to second power, so everything is now second power here. Now let's get everything outside of the square root. Square root of 9 is 3 and square root of 1 is 1, so you can remove the square root. And then we have x squared there. And further simplification, numerator is 4x squared, denominator is x squared. After cancellation, we get 4. Now, you have to be a little bit careful here because x is going to negative infinity. And do we have to worry about it in this particular case? The answer is no, because we have x squared, which is always positive, you see. If this had been odd power, that would have opened the door for another ramification because negative infinity to the odd power is negative infinity, not positive infinity, and square root is always positive, so you need extra negative sign. In this case, no, because we have even power. And good way to see that is actually to graph this thing. You see, you can use your graphing calculator, and you're going to get some graph kind of like this. And let's go a bit further. Negative 10 to positive 10. Okay, looks like a horizontal asymptote is forming at y equals to 4. Negative 50 to positive 50. Yeah, pretty clear, you see. Now, if you have two different horizontal asymptotes forming, then that's an indication you have to do some further work about changing the sign or things like that. This problem was not that difficult. By the way, if you use L'Hopital's rule here and then try to take the derivatives, you're going to get nowhere. Take the derivative and then you're going to be stopped at the very first step. When you take the derivative of this radical, you're going to get a mess. And at the time, you're going to know that L'Hopital's rule is not the right way to go because the purpose of L'Hopital's rule or any other technique, as a matter of fact, is to make the problem simpler, and you just made the problem worse. So you can see that it's not going out. All right, in that case, what do you do? I suggest asymptotic estimation. By the way, this is my solution. Solution 1. And then I'd better show you the textbook solution as well. I forgot about that. Let's talk about it. Okay, here we can divide everything by the highest order term. And then I'm dividing by x squared inside the square root, so I'm dividing by x to the fourth power. And then again divide by the highest order term, x to the second power, outside square root, so second power, inside fourth power. Okay, all right. And then the next step. Let's take just a little bit of simplification. Okay, just a little bit of simplification. Okay, this is 1. And that's 2. And then this is 1 over x. And then this is 9. And then this is 1. And then now this is 8 over x to the third power. This is okay. This is 7 over x to the third power. Okay, I guess everything is all set. And then we can apply the limit rule. 1 over infinity, that's going to 0. And 1 over infinity, that's going to 0. And that 2 is going to 0. That's going to 0. And that's going to 0. And consequently, what computation do I get? We have 1 plus square root of 9 over 2 minus square root of 1. And consequently, we just had 4 over 1, so 4. Okay, this is the textbook's method. If you want a little bit more theory, then this is a little bit better computation because instead of just asymptotic estimation, you're using all those limit rules. Do I recommend it? No, I don't. I prefer asymptotic estimation because the numerator and denominators are asymptotically equivalent to simpler functions by simply taking the highest orders. That's a little bit easier, and that's what I recommend. But still, if you want to use the textbook's method and use the second solution, go ahead and use it. Nobody is preventing you from doing that. That completes number 1 of this set, and let's do number 2 in a separate video.